Black holes have captivated scientists and the public alike for decades. These cosmic giants, with their immense gravitational pull, defy our understanding of physics and stretch the limits of human imagination. From science fiction to cutting-edge astrophysics, the idea of entering or escaping a black hole has remained one of the greatest mysteries of the universe. According to classical physics, nothing, no matter how fast, can escape a black hole once it crosses the event horizon. The gravitational pull is so extreme that even light, the fastest thing in the universe, is unable to break free. This has led to the widely accepted belief that black holes are one-way destinations, places where matter and information vanish forever. However, new theories are beginning to challenge this assumption. Recent advances in quantum mechanics, relativity, and speculative physics suggest that an escape from a black hole, while still improbable, may not be entirely impossible. Could there be hidden pathways, quantum loopholes, or exotic physics that allow something or someone to defy the laws of gravity? Scientists are beginning to explore these possibilities, and the answers could reshape our understanding of the universe itself. A black hole is a region in space where gravity is so intense that nothing, not even light, can escape its pull. It forms when a massive star collapses under its own gravity, compressing all its mass into an infinitely dense point called a singularity. Surrounding this singularity is the event horizon, the boundary beyond which escape is impossible. Black holes come in different sizes, from stellar mass black holes, a few times the mass of the Sun, to supermassive black holes, which sit at the centers of galaxies and contain millions or even billions of solar masses. Despite their immense power, black holes cannot be directly observed. Instead, scientists study their effects on nearby objects such as stars and gas clouds to infer their presence. The event horizon, the point of no return. The event horizon is the defining feature of a black hole. Once anything crosses this boundary, it is doomed to be pulled toward the singularity, with no chance of return. The closer an object gets to the event horizon, the more extreme the gravitational forces become, stretching and distorting it in a process known as spaghettification. From the perspective of an outside observer, an object falling toward a black hole appears to slow down as it approaches the event horizon, never fully disappearing from view. This is due to the warping of time caused by intense gravitational fields. However, from the falling object's point of view, it crosses the event horizon and reaches the singularity in finite time, with no way to escape. Singularity, the ultimate trap. At the heart of a black hole lies the singularity, a point of infinite density where our current understanding of physics breaks down. General relativity predicts that at this point, space and time cease to function in any meaningful way. However, quantum mechanics suggests that singularities may not be true infinities, and some yet unknown quantum gravity theory may eventually provide a more complete picture. The existence of a singularity raises profound questions about the nature of reality. If all matter and information are crushed into an infinitely small point, does that mean information is lost forever? This contradiction, known as the black hole information paradox, is one of the biggest unresolved mysteries in modern physics. Some scientists believe that resolving this paradox could unlock new insights into escaping a black hole, or even understanding the fundamental nature of space and time itself. The role of gravity and space-time warping. Gravity near a black hole operates in ways that defy common intuition. As an object falls toward a black hole, its time relative to an outside observer slows down due to gravitational time dilation. From the perspective of someone watching from afar, an astronaut falling into a black hole would appear to move slower and slower, never fully reaching the event horizon. However, for the astronaut, time would flow normally, and they would reach the singularity in a finite amount of time. Space-time warping is so extreme inside a black hole that escape trajectories simply do not exist. Even light, which moves at the absolute speed limit of the universe, has no possible pathway out once it crosses the event horizon. This is why black holes appear completely black. No information or radiation can escape under classical physics. Under the laws of classical physics, there is no way to escape a black hole once past the event horizon. All forces, no matter how powerful, would only delay the inevitable fall into the singularity. This is why black holes have been considered cosmic prisons, where anything that enters is lost forever. However, while classical physics paints a bleak picture, modern advances in quantum mechanics and speculative theories are challenging this view. Could there be hidden mechanisms, quantum effects, or even new dimensions that provide a loophole to the no-escape rule? Recent research suggests that black holes may not be as final as once. New theories challenging the no-escape idea. While general relativity describes gravity on a cosmic scale, quantum mechanics governs the subatomic world. The problem is that these two fundamental theories do not fully agree when applied to black holes. General relativity predicts that nothing can escape a black hole, while quantum mechanics suggests that information and particles might not be completely lost. This conflict has led scientists to explore new possibilities that could redefine our understanding of black holes and even hint at. In 1974, physicist Stephen Hawking proposed a groundbreaking idea. Black holes are not completely black. According to quantum mechanics, pairs of virtual particles constantly appear and annihilate each other in empty space. Near a black hole's event horizon, one of these particles can fall into the black hole while the other escapes as radiation. This process, now known as Hawking radiation, causes the black hole to slowly lose mass over time. If a black hole emits enough Hawking radiation, it could theoretically shrink and eventually evaporate. While this process is incredibly slow for large black holes, it suggests that black holes are not permanent traps. However, this raises a new question. If a black hole disappears, what happens to the information that fell? Some theories suggest that black holes may be connected to wormholes, hypothetical tunnels in space-time that could lead to another part of the universe or even another universe entirely. If wormholes exist inside black holes, they could provide a way for matter to escape, bypassing the singularity. However, current models suggest that naturally forming wormholes are unstable and would collapse before anything could pass through. Still, if advanced civilizations or future physics could stabilize them, they might offer a real escape mechanism. One of the biggest mysteries in black hole physics is the black hole information paradox. General relativity suggests that anything entering a black hole is lost forever, but quantum mechanics states that information cannot be destroyed. This contradiction has led to radical new theories, including the holographic principle, the idea that all the information entering a black hole may actually be stored on its event horizon, much like a hologram. If true, this could mean that information never truly disappears and might even be recoverable in some form. Some researchers believe this principle could be a key to understanding how information, and possibly even objects, could escape a black hole under the right conditions. While these ideas remain theoretical, they challenge the traditional notion that black holes are absolute prisons. The next frontier of physics may uncover ways in which black holes are not the ultimate dead ends we once thought they were. While no proven method of escaping a black hole exists, several speculative theories suggest ways in which matter, or even conscious beings, might evade total destruction. These ideas remain highly theoretical, but they push the boundaries. One of the most popular escape scenarios in science fiction is faster-than-light travel. If an object could exceed the speed of light, it might theoretically break free from a black hole's event horizon. However, according to Einstein's relativity, traveling faster than light is impossible under known physics, as it would require infinite energy. However, some physicists have proposed warp drives, theoretical constructs that could bend space-time itself. The Alcubierre drive, for instance, suggests that by contracting space in front of a spacecraft and expanding it behind, an object could travel faster than light without technically breaking the rules of relativity. If such a drive were possible, it might provide a way to escape a black hole, but current physics suggests the energy requirements would be astronomical. Some theories propose that exotic matter, substances with negative energy, could counteract the intense pull of a black hole's gravity. In quantum physics, negative energy has been linked to Casimir effects and Hawking radiation, suggesting that it may have real applications in manipulating space-time. If exotic matter could be harnessed, it might be used to stabilize wormholes or even create artificial space-time distortions that could allow an escape from a black hole's interior. While no known form of exotic matter exists in large enough quantities, this remains a fascinating area of study. Some physicists speculate that our reality itself might be a simulation or part of a larger multiverse. If true, then escaping a black hole might not be a matter of physical propulsion, but rather a shift in dimensions or realities. One idea is that black holes could serve as gateways to other universes. Some models suggest that matter falling into a black hole doesn't simply vanish, but instead reappears in a different region of space-time or even in an entirely new universe. If this theory is correct, entering a black hole might not mean destruction, but rather transition into another realm of existence. At present, all these escape scenarios remain purely speculative. While current physics strongly suggests that no escape is possible, ongoing research in quantum mechanics, relativity and cosmology may eventually reveal new loopholes. What seems impossible today could become reality in the distant future. If humanity ever unlocks the secrets of space-time manipulation, the dream of escaping a black hole may not remain science fiction forever. While black holes remain some of the most mysterious objects in the universe, ongoing scientific research and technological advancements are bringing us closer to understanding their nature. These efforts could one day reveal whether escaping a black hole is possible, or if new physics beyond our current theories might allow it. Observing black hole behavior. In recent years, scientists have made significant strides in directly studying black holes. The Event Horizon Telescope, or EHT, captured the first ever image of a black hole's shadow in 2019, providing groundbreaking observational evidence of their structure. By continuing to observe black holes and their interactions with surrounding matter, scientists hope to uncover new insights into how they function. Future telescopes and space probes could offer even clearer images and data on black hole environments. If we detect anomalies, such as unexpected energy emissions or possible leaks of information, it might hint at previously unknown escape mechanisms. Advancements in quantum gravity theories. One of the biggest challenges in physics today is unifying general relativity, which describes gravity on a large scale, with quantum mechanics, which governs the microscopic world. Many researchers believe that a quantum theory of gravity, often called a theory of everything, could provide answers about black holes that current physics cannot. Some of the leading approaches include string theory, suggests that black holes may not have true singularities, but rather complex structures made of vibrating energy strings, which might allow for novel escape routes. Loop quantum gravity proposes that space-time itself is made of tiny loops, potentially preventing the formation of singularities altogether and offering alternative paths out of a black hole. Holographic principle implies that black hole information is stored on the event horizon and may not be lost, possibly allowing for information retrieval or even a form of escape. The role of AI and supercomputers in space-time research. The complexity of black hole physics requires immense computational power to simulate and test different theories. Supercomputers and AI are now being used to model black hole dynamics, including how matter behaves near the event horizon, and whether quantum effects could provide an escape mechanism. With advances in machine learning and quantum computing, future research might uncover hidden patterns in black hole data that challenge current assumptions. If a new theory emerges that allows for black hole escape under extreme conditions, it could revolutionize our understanding of space-time itself. As technology and theoretical physics continue to evolve, our understanding of black holes will deepen. While no concrete evidence currently supports the idea of escaping a black hole, scientific discoveries in the coming decades could change that. Whether through quantum breakthroughs, new cosmic observations, or entirely unforeseen developments, the question of whether we can escape a black hole remains one of the most intriguing mysteries in modern physics. The idea of escaping a black hole has long been considered impossible under classical physics, but emerging theories challenge this assumption. General relativity tells us that once something crosses the event horizon, it is trapped forever, doomed to be pulled into the singularity. However, advancements in quantum mechanics, speculative physics, and cosmic observations suggest that reality may be more complex than previously believed. Hawking radiation introduces the possibility that black holes are not permanent prisons but slowly evaporating entities. Theoretical constructs like wormholes, warp drives, and exotic matter hint at potential escape routes, though none have been proven or observed. The information paradox raises profound questions about whether black holes truly erase everything they consume, or if there is a deeper mechanism at play that preserves or even allows for the recovery of information. Scientific research continues to push the boundaries of our understanding. Observations from telescopes, supercomputer simulations, and ongoing developments in quantum gravity may one day provide an answer to the question, can we escape a black hole? While no concrete evidence suggests an escape route exists, the universe has a way of surprising us. The more we learn about black holes, the more we may discover about the true nature of space, time, and the fundamental laws governing our reality.